Welcome to the second session of Week 6 Supply Chain Design course. This session will focus on Phase 2 and 3 Supply Chain Design Decisions. In the previous session, the warehouse location problem-based approach supports the identification of regions that should be considered for setting up a supply chain. These regions might be continents, countries, states, or even farms, or growing areas, or plantations supplying or consuming products. According to the location planning scheme outlined in the slide of Supply Network Design Framework, the outcome of phase number 1, those are regions to be considered in the prospective supply chain design, are forwarded into phase 2, where one or several locations have to be identified for each region as network node. In the context of the PowerPoint Sport case study, the regions are the countries that host the resellers or the markets. A typical phase 2 decision is now to select a warehouse to which the packages are shipped from China and from where customers in the market receive their deliveries. We can now assume that the regional resellers' existing facilities are too small to handle the additional freight flow associated with the celluloid-free balls, and the resellers is looking for a new location in the associated country to build or rent a new warehouse. This section addresses the particular problem of identifying promising candidates for establishing a new facility that can handle incoming and outgoing materials as part of the global supply chain. In particular, by considering available demand knowledge, we will use center of gravity representing a phase 2 decision situation, developed simple mathematical calculation for the identification and determination of the coordinates of an optimal location. Now let's go to the next slide. Let's look at a table in our slide. There are 5 customers of TT Profi from Germany with different locations and demand sizes. Each location is represented by an ordered pair of x and y coordinates. The x and y coordinates of the 5 locations are given in the third and fourth columns of the table. These data cannot be modified. They are input data or problem parameters. The coordinates of customers I are named xi, yi. For instance, x1, y1 stands for 10, minus 80, and so on. Demand for each customer is also given and denoted as dxi, yi. In contrast, the x, y coordinates, that is px and py, of the new warehouse are variable and have to be determined. Consequently, px as well as py are the decision variables that signify the location of distribution center that has to deliver ping pong balls to those 5 customers in the investigated decision scenario. The objective of center of gravity method is to minimize the total transportation cost by considering the location of markets expressed by 2 coordinates, demand or volume of goods shipped to those markets, and shipping cost or distance, by assuming that cost is proportional to distance and volume shipped. In application, we could get the coordinates from Google Maps in a form of longitude and latitude. One assumption of center of gravity method is that the total transportation cost sum is proportional to the distance and the transportation volume, for instance the demand. This leads us to the formulation of objective function as follows, that z is the total transportation cost as a function of x and y, the coordinates longitude and latitude, that is equal to the sigma, the summation of the small d that is a distance between the central warehouse, that is px and py, that's the coordinate for central warehouse, and the a particular market location xi and yi. Then multiply by the demand at a particular market d, that is xi and yi. Right? The running index of markets number I started from 1, and therefore n is equal to the total number of markets minus 1. Okay? Now how to compute center of gravity method? There are two ways of calculating the distance between market and central warehouse. First is direct line by taking Euclidean distance between these 2 points in the plane, and the second is corner method, as is the orthographic or square distance calculation. And we can see that there are two different formulation for direct line methods. That the Euclidean distance actually is like direct distance between 2 points, and without going right or going left, just straight line from between 2 points. Now, in direct line methods, the coordinates are calculated as follows. First, for finding access of central warehouse, for numerator, we need to multiply the demand at each market with access and divide it by the Euclidean distance between that particular market J, for instance, and particular central warehouse location P. For denominator, we just divide demand at each market and divide it by the Euclidean distance between that particular market J and potential central warehouse location P. Similarly, for finding ordinate location of central warehouse, for numerator, we need to multiply the demand at each market with the ordinate of a particular market and divide it by the Euclidean distance between that particular market J and potential central warehouse location P. For denominator, we just divide demand at each market and divide it by the Euclidean distance between that particular market J and potential central warehouse location P. Corner method is simpler. For finding access of central warehouse, the sum of multiplication between demand of each market location and its access is divided with the sum of demand from all market locations. Similar way for ordinate. Sum of multiplication between demand of each market location and its ordinate is divided with the sum of demand from all market locations. If cost is different for different transportation links, then cost can be added as additional variables. Now let's take a look at an example from our case study. Here we have 5 location of customer. Sport 123 Kilo, TT Direct, Sport and Fun, Laser Outlet and Rackets and more. And each of those markets has its own coordinates xi and yi. Next, we calculate distance between particular market location and potential central warehouse location. First, before finding the distance, we need to find the coordinates of central warehouse location. In the above equation, we have px and py. We have also numerator and the denominator. For instance, px equal to 30 minus 45 plus 90 plus 157.5 minus 150 divided by 11, and we have 7.5. That is the access of our central warehouse. But the question is that where are those numbers come from for both numerator and denominator? Now we can back to our previous slide. Here, for corner method, we have px. The formulation for px, it is a summation between demand at a particular market times its abscess and then divided by the total market demands. And therefore, we have the total market demand, actually 3 ton plus 1 ton plus 1.5 tons plus 3.5 tons and plus 2 tons. And if we calculate the summation of all this number, it results 11 tons. And what about the 30 and then 45 minus 45 and then plus 90 plus 157.5 and minus 150? 30 coming from tens times 3 tons, and we have 30. Minus 45 times 1, and we have minus 45 here. 60 times 1.5, and then we have 90. 45 times 3.5, and then we have 157.5. And finally, minus 75 times 2, we have 150. And then we have the following number. We do the same for the ordinate of central warehouse, and then we found minus 27. And we use this number to calculate the distance. Alright? Now finally, we have to calculate the total transportation cost. We back to our previous equation for total transportation cost as follow. That the summation of a distance times the demand at a particular market location. And then we have the following computation. 55.5 times 3. 55.5 times 3. And then plus 55.5 times 1. 129.5 times 1.5. 85.5 times 3.5. And 189.5 times 2. Finally, we have the total transportation cost at 1094.5. However, we have to note that an assumption that cost factor per kilometer and weight unit is 1 euro. If not, we need to multiply distance by volume by cost factor, as we have in the previous slide here, cost factor, right? Finally, we go to stage 3. That's location selection and factor rating method. In phase 3, the supply chain pinpoints the exact location in a particular country and region. About the location of facility establishment, decision elements are not limited to only cost or distances, but a wider variety of factors can be included in the analysis. In our slide, we have 7 steps in the method to find the exact location of our central warehouse. First, we should have several options of location of our central warehouse in order to compare which one the best. Or maybe we can have not only 2, but can be 3 or 4 and 5. Second, we have to determine decision criteria about location factors and their measurement. about the criteria, we will see in the next slide what kind of criteria to be used. And then we have to determine weighting totaling 100% for different criteria. And then we evaluate every location option on a normalized scale to achieve partial utility values. For instance, the use of a scale from 1 to 10, in which 10 is best, or maybe 1 to 5, 5 is best, depending on what scale we use. If we use, for instance, a Likert scale, then should be 1 to 5. Or maybe we can use not numerical, but also verbal scale, like good, very good, bad, very bad, or just so-so, or something, some kind like that. And we have to also to calculate the total utility value of a location option by multiplying partial utility values with weights and adding these values. And then we compute weighted average if many experts are involved. It is a bit complicated because we combine both qualitative and quantitative methods. And that also signifies that finding exactly the location for our facility is not that easy because it comprises many factors to be included, including experts' opinions. And finally, we choose the option with the highest total utility value. These are qualitative and quantitative factors that are involved in determining the exact location of our central warehouse. For instance, but it is not limited to only this criteria. We have also other, and you can add based on your specific situation in finding warehouse locations or any other supply chain facility location. First, for quantitative criteria, we have transportation cost, also building and construction cost, rental cost, labor cost, material cost, taxes, financial support from local governments. That is quantitative criteria, meaning that we can get the number from many parties to compare. For instance, about the rental cost. Is it cheaper to build a factory here in Limerick as compared to Dublin, for instance? Or is it cheaper to get labor from this area as compared to Dublin? That's we can get from a statistic company or maybe from many sources in our government to compare with the criteria about the labor cost and rental cost. Another kind of criteria that is qualitative criteria, that is infrastructure, quality of labor, transportation development, purchasing power, option for financing, suppliers, political risks, natural disaster risks, proximity to customers and suppliers, business climate, environmental regulation, competitive advantage, and finally government and trading barriers. All of these criteria we cannot get like exact number and compare peer to peer between one and other options of facility location. However, we can involve experts to evaluate, also to make comparison about this criteria. And therefore, by using all together these two types of factors, qualitative and quantitative factor, we have to combine both experts' opinions and also from statistical data. Now let's start with example in our slide. In our slide, we have three options of location about our central warehouse, X, Y, and Z. And also we have several factors to be considered. For instance, infrastructure, proximity to suppliers, proximity to existing sites, expansion potentials, quality of labor, and topography. Each factor has different weight of importance. For instance, infrastructure has 35% degree of importance. Proximity to supplier has 20%. It is the same as proximity to existing sites. expansion potential, and quality of labor share the same weight at 10%, but topography has least weight as compared to others at 5%. For each option X, Y, or Z, a panel of experts evaluate their points and give points to each of those factors. For instance, for infrastructure, X has 0.7 from a range of score from 0 to 10. Y got 0.8 and Z got 6, meaning that Y in terms of infrastructure is the most favorable. And also proximity to supplier. X got score 6, Y 7, and Z 8, meaning that in terms of proximity to suppliers, Z is the best. And also other factors are evaluated with the same way by a panel of experts. And then, in order to find total utility value for infrastructure, for instance, we need to calculate weight time points to get partial value. For instance, the partial value of infrastructure is 2.5, 2.45. For option X, it's coming from 35% times 7. For Y, we have 2.8 coming from 35% times 8. And we do the same for other factors for each option. Finally, the sum of partial value for each option is the total utility value for each option. And then we compare for all options the total utility values. And the highest total utility values will be chosen as a potential location of our central warehouse. And in our case, option Z is the best, and we choose that. However, it is suggested if the score of different options are very close to each other, sensitivity analysis is mandatory. For instance, between X and Z, 7.15 is not that far from 7.45. For instance, if one factor is changed a little bit about its point, for instance, proximity to existing sites of Z, because of some construction in that area, and therefore the point degrade from 9, for instance, to 6, is Z is still the best option. And also in terms of let's say expansion potential, because of the location where Z will be built, the facility will be built is very popular, and therefore the previous evaluation of expert is not anymore valid, and then we have to degrade the expansion potential from 7 to 4. Is Z still the most favorable option? And therefore, shortcomings of the factor rating method include the fact that the weighting percentages assigned per factor are not clearly visible. It must be updated frequently. In order to conclude our lecture today, in order to design a supply chain analytically, several factors are considered. For instance, variable cost of transportation, inventory, fixed cost of facility establishment that depends on many parameters such as annual demand at markets and capacity of potential sales, storage capacity, supply chain networks structure. The solution of supply chain design needs a support from optimization and simulation tools, which can be deterministic but maybe not so realistic, or stochastic but also more complicated to find an optimal solution. Those are the challenges in supply chain design. This is the end of our lecture today, and see you in the next session.